So here we're given a kite. Actually, that area of the rhombus formula we were talking about, that area equals 1/2 diagonal 1 times diagonal 2. That's actually true also for a kite. And a rhombus is a special type of kite. Remember, a kite is two adjacent sides that are congruent. So we have this 10 and this 10, and then these two adjacent sides. Kites have diagonals that are always at right angles to one another. So, same kind of idea I just talked about with the rhombuses in the last video is what we could use for this one. Approach 1 is to just bust it up into pieces of triangles. And so, because these are right triangles here, we can get the pieces here. So this right triangle is going to be, you can use Pythagorean theorem, or it's going to be a multiple of 3, 4, 5. I can see it's going to be 6, 8, 10 is a multiple. So 6, 10. So this diagonal is going to be 8 right here, or 16 in total, 8 of each, because diagonals are bisected in that particular one. So if we wanted to use the formula here, area equals 1/2 diagonal 1 is 8 plus 8, which is 16. Diagonal 2 is 6 plus 12, which is 18. And so 1/2 of 16 is 8 times 18. And 8 times 18 is 144 units squared. You could also just think of this as, actually one way to do this is to just think about it as two triangles here. If I draw this triangle here, KET, the area of a triangle is 1/2 base times height. The base of this triangle, since I have this height here, the base is 6 plus 12, so 18, and the height of this triangle is 8. But I have two of them because I have this one on this side, so I can multiply that whole thing by 2. So the area of my trapezoid is going to be 1/2 18 times 8 times 2. 1/2 of 2 is 1. Those will cancel then. 18 times 8, you can see it's the same number there, is 96. So again, approach 1 is to memorize the formula. Approach 2 is to just think about the triangles and bust it apart that way and add up the pieces. So this is going to be a compound area problem. I talked about the big plus little. In this case, I think we're going to I always like to find parallelograms and triangles and see if I can add up the pieces. So let's do that here. I'm going to draw this over to make a rectangle. And so it looks like my goal now is going to be to find the area of the rectangle, which I'll call region 1, and the area of this triangle, which I'll call region 2. Well, we have the base and height of this rectangle, so the area of 1 is going to be just base times height, which will be 3 times 7, which is 21. And now we have to see if we can figure out the area of this triangle here. We're going to have to back into a couple pieces here. So if I draw this segment up here, we know that this side of the triangle has to be 3, because the whole thing has to add up to 7. So we have 3 there, and then the side of this triangle, if the whole side is 5 and this part is 3, 5 minus 3 is 2. So the area of region 2 is going to be 1/2 base height because it's a triangle. Base, since it's a right angle here, we can use base of 3, height of 2, and I forgot the 1/2. So 1/2 times 3 times 2 is 3, so that little triangle here is 3 square units. The rectangle is 21. We add those together to get 24 square centimeters. So finding areas of regular polygons is typically an exercise in just finding areas of triangles and then adding them up. So that's what I'm going to do here. I'm going to draw myself a regular hexagon. And then what I like to do is just draw one of those triangles. I can see that if I do this all to the center, I'm going to get 5 triangles that are identical, but let's work on just one of these triangles and see if we can get the answer here. So, because then we can just if we get the area of one of the triangles, we can multiply it by 6. So find the area of a regular hexagon with side length of 22. So all these sides are 22, but in particular for this triangle that I'm focusing on, the base is 22. And apothem, that's a definitional thing, but the apothem is always starts at the center of a regular polygon, and it's the perpendicular distance to a side. So that apothem there is 19.1. And conveniently, if we just focus in only on this triangle, we have a base and we have a height, so we can find the area of it. Area equals 1/2 times 22 times 19.1. And 22 divided by 2 is 11, so it's 11 times 19.1. And if you put that in your calculator, you'll get 210.1. And again, this 210.1 is just the area of this shaded rectangle, or shaded triangle. We have 6 of them, so we have to multiply our answer by 6 to get the full area of the hexagon. And if you put that into your calculator, 210.1 times 6 will give you 1,260.6. And these are inches, so we have inches squared. And so that is the answer. So 84, this is really the same approach as the prior problem, except it's not, the apothem is not given, so we have to actually do some work to get the apothem. So I'm just going to draw the same exact picture I drew on 83. A regular hexagon, and this is the triangle we're focusing on, and this side is 2, and we're trying to find this length. Well, recall that when you're trying to find missing pieces of right triangles, you typically have 2 ideas you can use. One is Pythagorean theorem, maybe can help, right triangle trig, or some of our special right triangles like 45, 45, 90. And it turns out that that's what's going to be useful here. Is in a hexagon, if we think about these interior angles here, if I draw all these in, all of these angles have to add up to 360 because it's a full circle. So the angle for this particular triangle is going to be 360 divided by 6, so that's going to be a 60-degree angle there. Since this is a regular polygon, I know that these are congruent sides, and so these 2 angles are also congruent because it's an isosceles triangle. These 2 have to add up to 120, so they each need to be 60. So I know I'm working with an equilateral triangle here, so all these sides are 2, and I think that's the idea behind this picture, maybe. Well, I guess you can't really tell it's 2, but so anyway, we have an equilateral triangle, so this problem turns into finding the area of an equilateral triangle with side 2. So if I do that, so we're going to find the area of this shaded guy here. I'm going to redraw it separately just to make it clear what's happening. We have the base of 2, the sides of 2. I'm drawing in a height. We know that the angles are 60 and 60. And so you can use your special triangle relationships here. This is the 30-degree angle. We know that the side across from 30 is always 1/2 the hypotenuse. So that's 1. Not surprising because the whole side is 2 and it should get bisected. So we have 1 and 1. And that means the height here is √3 because that's the pattern. Take the smaller side times √3 gives you the longer side across from 60. And so we have a height of √3. So the area of this triangle, 1/2 base times height. 1/2, the base is 2. The height is √3. 2 divided by 2 is 1, so it's just √3. But remember, we have 6 triangles we have to account for here, so we're going to multiply this whole thing by 6. 6 times √3 is 6 √3, which will get you an answer of D. Now this one's kind of a definition-heavy one, so we have this idea of what the radius of a polygon and an apothem of a polygon. So we have an equilateral triangle, a 3-sided regular polygon, and we're going to think of this as being inside of a circle, and there's the center of the circle. It's not at the center of the triangle, but it's, I'm not going to see if I can draw this very well. And so what this is telling us is that the radius is 8, so the radius of a polygon is out to a vertex, so that's 8. If I had a square, this would be the radius. If I had a hexagon, this would be the radius. So that's just trying to put it in context here, because sometimes it's hard to see what a radius means in terms of a a triangle. And then we have an apothem. The apothem is the perpendicular distance to a side. So this would be 4. Like in a square, this would be the apothem. In a hexagon, this would be the apothem. So just to see the parallel with different figures to show you what radius and apothem are. So now we're trying to find the area of this triangle with these measures. So just like the hexagon problem we just did, if I draw this in at 8 here, and we know this is also 8, you can see that we get 3 equally sized triangles here. So what I'm going to do is the same idea. I'm going to just focus in on one of these triangles, this one right here, and see if I can find the area of it. I'm going to redraw it here. The height is 4 and this side is 8. Well, because of this leg is half of this leg, we know we're in a 40, 30, 60, 90 triangle situation. You could also use Pythagorean theorem, but in any case you'll get that this side is 4 square roots of 3. Again, you either remember 30, 60, 90, or if you wanted to, you could find it by doing 8 squared minus 4 squared equals I'll call it b squared, and you would get 4 square roots of 3 by solving this for b. That's only one side of it though, so we have the other side here, which is also 4 square roots of 3. And so now we have what we need to find the area of this triangle. Area equals 1/2 base times height. The base is 4 square roots of 3 plus 4 square roots of 3. So that's 8 square roots of 3. The height is 4. 1/2 of 4 is 2. So 2 times 8 root 3. 2 times 8 is 16. 16 root 3. Now again, we found the area just of one of these triangles. We have 3 of them. We have to multiply our answer by 3. 48 root 3, which would give us an answer of D. Area of a regular pentagon with a radius of 10. This is a challenge problem because you'll see it's going to involve some trigonometry in order to solve this. We can't just use 30, 60, 90 triangles. So, same approach. We're going to divide this up into triangles and focus in on one. So let's focus in on this one right here. The radius is 10, so we know that this value is 10, and that's all we know. So we're trying to find the rest of this triangle. So the first thing we can do is I'm going to draw the shaded triangle right here. We know the radius is 10, and I'm going to draw in this right here. So in order to find the area, we need actually this base and this height. We have neither of those things. But what we can do is use trigonometry. So if we know, the same idea, if we know that all these angles here have to add up to 360, and how many of them are? There's 1, 2, 3, 4, 5. So each one of those points there has to be 360 divided by 5. So this full angle here is 72. If this angle is 72, right here, this full angle is 72, I can then find these two angles down here, because I know 180 minus 72 and that's 108. And those two have to add up to 108, and I know they're equal because this is an isosceles triangle. So 108 divided by 2 is 54. So that'll give me 54 degrees as that angle right there. Now we can use trigonometry. So what I need the base and I need the height. So let's call this one H here. How do we think about SOHCAHTOA to help solve this problem? Well, if I focus in on this angle, 54, I have the hypotenuse, and I'm looking for the opposite. So I want something that has the O and the H in it. Well, SOHCAHTOA, sine is what's going to help us here. So sine of that angle, 54 degrees, is going to equal opposite, which is the hypotenuse, opposite, which is the height, and hypotenuse, which is 10. So the height of this triangle will be, let's multiply both sides by 10. 10 times sine 54 degrees. So I put that in my calculator. You'd get 8.09 approximately. I'm going to use 2 decimal points because I want to round at the end. And now to get the next part here, I'm going to call this little part of the right triangle here B, this bottom base, which is half of the equilateral. That's adjacent to 54, and we know that 10 is the hypotenuse, so we want something that's going to involve adjacent and hypotenuse. Well, we know that that's cosine, so cot TOA. So cosine of 54 degrees is going to be B, which we're trying to find, divided by hypotenuse, which is 10. And so B is going to be 10 times cosine 54 degrees, which at 2 decimal points is 5.88. So if we look at this triangle here, we have the height. In order to get the full base, we need to do times 2. So the full base is 5.88 times 2, which is 11.76. Sorry, it's hard to see there. 11.76. And so now the area of one of these triangles is area 1/2 base times height, which the base is 11.76, whole base. The height, which we found up here, 8.09, and we plug that into our calculator, and you'd get 47.57, and that's just for one of the triangles, and so we need to multiply our answer by 5, because this is a pentagon. There's 5 of those triangles. 47.57 times 5 is 237.84, which rounded to the nearest tenth is 237.8, and that's meters squared.